Okay, there we go. So, we've kind of set the background at this point with the different trigonometric functions, but, obviously we still have a little bit more to talk about it. And that's kind of what the second half of chapter 1 is going to do, is we're going to get a little bit more detailed with these functions. So let's begin with the graphs for these sine and cosine functions. So, a lot of times we talk about the sine curve, the cosine curve, the tangent curve. So obviously these are all based off of the graphs, for these functions. So you can see right here on the screen, the very first graph you are looking at is going to be the graph of the sine function, which is what we call as the sine curve. And we had talked about the period for sine and cosine functions. So remember, the period for both of these functions is 2 pi, which means, you basically come back a full circle. If you're looking at a unit circle, you basically come back a full circle and you're back at the beginning, where your sine and cosine values will start becoming the same. Those ordered pairs will start looking the same. So when you make that one complete rotation, we talk about that as being your period. So you can see what happens when we look at the graph of a sine function here is, this is where the origin, the starting point is. So your ordered pair here is going to be 0, 0. And then you can see when we come back and complete this one single period, we land back on the x-axis, and here your x value is 2 pi, but your y value is going to be 0. And so this, going from the origin 0, 0 to the 2 pi, you can see this forms one period. And in this case, we get one maximum and one minimum value on our function. So you can see our maximum here corresponds with positive 1 on the top. The minimum value here corresponds to negative 1 on the bottom. So, that gives you your maximum minimum value, and you will see right in the middle, we end up back at the x-axis, where you have pi. And you can look at these ordered pairs, and, you can kind of transpose them on the unit circle too, because, those values will match, but, obviously this is a graph and that's just the values on the unit circle. So one thing to kind of keep in mind is that, these functions, basically this graph keeps repeating. So this shape that you're seeing, where we start at the x-intercept, we go to a maximum value, come back to the x-intercept, go down to a minimum value, and then come back up to the x-intercept. This shape will keep repeating indefinitely as you go to the right and as you go to the left. So a lot of times when they're asking you to graph these functions, they may say it for, do it for 2 periods. So, you would basically make sure that this shape that you're seeing in the one period from 0 to 2 pi, you basically repeat it twice. So that way, we kind of get a general idea of the shape of these functions, but that's kind of what happens. So you will see they're saying this basic sine curve will keep repeating indefinitely as you go to the left and to the right. And, this will be the same thing that's going to happen with your cosine function also. The only difference is, the graph is going to look a little bit different from our sine curve over here. So let's take a look at our cosine graph, and I'll try to keep these guys. I might have to make this a bit smaller so you can kind of see both of these on the same screen. Let's make it a little bit smaller. So the big differences here is, obviously, again, the cosine function also has a period of 2 pi. So you will see, again, this is what the cosine function looks like. And of course, this is where our sine function was. So the biggest difference is the sine function begins right here at the origin, whereas the cosine function, instead of starting right here where the cosine sine function did, your cosine actually starts at 0, 1. So right over here. So you will see this is actually where we have the maximum point on our function. You go down to the x-intercept. We then get down to a minimum. We come back to an x-intercept, and then you end up back at the maximum. So you're still making this shape, but not in this order, because we actually start at, that half of that maximum at this point 0, 0. And, of course, we end up at 2 pi again. And you end up at 2 pi and 1. And of course, this guy here is at 2 pi and 0. So, just a little bit of difference, but you will see we still have that general shape of the sine curve, but, it just has a little bit of a different orientation in terms of where your maximum minimum points are going to be and where it's going to intersect the x-axis at. Now, for both of these functions, as far as the domain goes, remember domain is the x values. It's going to be all real numbers, which means the x values for both the functions can be any real number. As far as the range for both your sine and cosine functions goes, you are actually going to stay between -1 and +1, including the endpoints. Because you can see, obviously, at +1, we have, function values. So all of these are going to be at +1. And then at -1, you have the lowest values, the minimum. So your range stays between +1, -1 for the sine function. Same thing for the cosine function, because again, at +1, we have all the maximum values. And then at -1, we have all the minimum values. So for both functions, sine and cosine, your domain and range will stay the same. Now, if you do any transformations or any modifications, that can change these values, but we're just talking about the basic sine and the basic cosine function and what those range and domain values look like for these. Okay, so let's clear this out for now. And you can kind of read, some of those details is mentioned in here in the text that you can read at. One other thing I wanted to point out was, and we can make this guy a little bit bigger. So the one other thing I wanted to point out was the symmetry of these functions. So your sine curve is going to be symmetric with respect to the origin, and the cosine curve is going to be symmetric with respect to the y-axis. So what do we mean by that? So if you look at the sine function, here is the origin. So the idea is, if you were to, try and look at the distance from the origin. So let's pick this point over here and, this point over here. If you try to calculate this distance between the origin and the point on the bottom and the origin and the point on the top, this distance is going to be the same as this distance over here. And you can do this for any point on the graph, so we could pick this point right over here and pick this point right over here. So if you calculated this distance and the distance on the other side, this distance would be the same as this distance. So this is what we're talking in terms of symmetry with respect to the origin. For the cosine function, we are saying we have symmetry with respect to the y-axis. So it's actually with respect to this. And this is actually easier to imagine. You can still do that distance thing if you wanted to anywhere from the y-axis. So if you took the point here, if you take this distance to the right and this distance to the left, it will be the same. You can do that same thing with the y-axis, pick this point over here and this point over here. So if you measure this distance and this distance, it's going to come out to be the same. Or the easiest thing would be if you fold your graph along that line where the y-axis is, your two halves are going to be perfectly coinciding with each other. Think about a parabola, right? That opens up or down. It's the same thing. You have symmetry, with respect to that vertical axis. It can be the y-axis or any other line. If you fold along that line, your two halves are going to match exactly in the same way. So that's your symmetry in terms of the y-axis. But with the origin, you can't really do the whole folding thing. So with the origin, it's easier to think about distances from that 0, 0 point. And this happens because, remember, we had talked about this, I think in section either 1.2 or 1.3, where we had said the sine function is an odd function. And remember, this is where you had the negative sine of t is equal to sine of negative t. That's because your Sine is an odd function, and odd functions have symmetry with respect to the origin. Cosine is an even function. So these guys have symmetry with respect to the y-axis. And in this case, you will remember that rule was if you had cosine of negative t, it still comes out to be cosine of t. And this can be literally visible right over here. Let's, so think about this. This is, if you did cosine of pi halves, it will come out to be 0. And this guy here is negative pi halves. And if we did cosine of negative pi halves, it is still going to come out to be 0. For that matter, we can do, let's scoot this down a little bit more. We can do this value over here. So this is in terms of pi and negative pi. So if you did cosine of pi, that will come out to be -1. You can do cosine of negative pi and it will still come out to be -1. So, this is where you can see cosine of negative t is the same thing as cosine of positive t. And this happens because these are even functions. With the sine functions, because they are odd functions, your sign changes. So since this is an odd function, let's pick this point here that corresponds to positive pi halves. And let's pick this point here, which corresponds to negative pi halves. So you can see sine of pi halves, and that's the positive pi halves, is going to be +1. And if we did sine of negative pi halves, this guy comes out to be -1, because for this one, remember, sine of negative t is equal to negative sine of t. So, if you have sine of pi halves and I just put a negative in front, that will actually make your answer negative, and that's what we have over here. So the difference between odd and even functions. So remember, cosine and its reciprocal function, which will be secant, are the only even functions. Cosine, sorry, I think I said that backwards. So cosine and secant are even functions. Sine, cosecant, tangent, cotangent. The remaining 4 are all odd functions. Okay, so you will see those properties for odd functions as the same ones. And if you want to get a little bit more background on these odd and even functions, go back to chapter P, and you will see a little bit more the algebraic definition for odd and even functions that you can look at. Now, when we talk about actually sketching these graphs, we have to use what we call as the 5 key points to help us, graph these functions. So these key points will actually tell us where the x-intercepts are, or it can also be y-intercept, something like this, where your maximum and minimum points are. So that can actually help us, see what the shape of our graph is going to be, where we are going to have the maximum points, where the minimum points, and where the intercepts are going to be. And you can see they are in different locations for your sine and cosine function, because even though you are going from 0 to 2 pi, you can see how different these two graphs look within that same period. So let's go over this example here in your handout, and then we'll pick one example from the textbook. So this one is actually talking about sketching the graph for 2 times sine of x, right? Because we know what the basic sine of x looks like, but what happens when we multiply by 2 in the front? So what you start out by doing is you take your period of 2 pi and you divide it into 4 equal parts. So basically start by 2 pi, divide by 4. 2 goes into itself once, goes into 4 twice. So you end up getting pi halves. We of course start at 0, 0. So the first thing we're going to do is come up with these x values. So you start with 0, then you, add pi halves to it. So that will give you 0 plus pi halves, of course, will be, at pi halves. And then you keep adding this factor of pi halves. So now that we're at pi halves here, go ahead and add another pi halves to it. So same denominator, pi plus pi will become 2 pi. The 2's cancel out, leaving you at pi. So this will be our next x value. Go ahead and add another pi halves to this. So this will end up giving us 3 pi halves, which is our next x value. And then of course we add another pi halves to it, which will give us 4 pi over 2. Clean that up into 2 pi. And you can see that's how we divide the period of 2 pi into 4 equal parts. But 4 equal parts means you're going to have 5 key points that you will be working with. And then you start plugging this, these x values that you came up with. Plug this in for the x value here in your function, calculate your y, and then based on that, if you land at 0, you're going to be at the intercept. If you end up at a positive number, that's your maximum. If you end up at a negative number, that's your minimum. And then of course, all the zeros will lead you to your intercept. So you can see now, once we get all of these ordered pairs, well, now we can go ahead and graph our function. So before I show you the graph, just to kind of show you what this would look like. So here's our 0, 0, pi halves, pi, 3 pi halves, and 2 pi. So you can see at 0, 0, we're still at the origin. Pi halves, you're going to be at 2. At pi, we're back at 0. 3 pi halves, we're going to be at negative 2. And 2 pi, we're back to 0. So you can see the only difference that happens here is instead of being where your original function was, because the original function goes from -1 to +1, the original function would be more like this. But because we're multiplying by 2, it actually increases the amplitude. So it actually makes those maximum and minimum points a little bit higher or lower, you know, on the negative side when you multiply by that 2 in front of it. So you can see this is what that graph ends up looking like. So in the gray is that original sine function, and then in the black is the function that we were graphing. So that's why, you know, these key points are important when you're trying to graph these functions, because they really can help you see what the shape of your graph is looking like. And they asked us to graph this on the interval from negative pi to 4 pi. So that's why you can see we are getting at least 2 full periods over here, and then, you know, just a little bit extra on the left-hand side. But at least you are getting 2 full periods to see that shape repeating, you know, as you go from left to right. So it's a little bit of a different graphing techniques than, you know, what we're used to in algebra, where you do those X and Y tables. And, you know, you just use those points. It's kind of the same idea, but we just stick with those 5 key points when you're trying to graph these functions. So you can see there's an example in your handout where they're having you work on 2 times cosine of X. So as you can imagine, just like you saw with the sine function, here with the cosine function, you know, instead of going with 1, you will be at 2 and -2. So these guys will again, you know, that amplitude will increase as you graph this. And you can see that in our video lecture if you wanted to see what that 2 times cosine of X looks like. But let's pick one from here. And I know they're kind of getting into the amplitude and period, and we'll come back and talk about that. But I just wanted to pick an example just to kind of show you what the graph would look like. So we haven't quite talked about adding these numbers. So I guess we'll do 25. And as you can imagine, just by seeing the example in the textbook, you know what this guy would end up looking like. But let's do number 25 here. So they're doing the f of x as sine of x as sort of like, you know, okay, this is what the basic function looks like. And then when we change it to 4 times sine of x, what that function will end up looking like. And you will see they're asking us to include 2 full periods, when you graph these functions. So let's take a look at this guy here. And for this one, what I'm going to do is actually open up our OneNote here and work on this graph over here. Let's take a look. So this guy was what, number 25? So they're asking us to graph the sine of x function and the 4 times sine of x function. So remember, the period of the sine function always goes from 0 to 2 pi. So basically we would say the period is 2 pi. So just like I showed you before, if you had to break this down into 4 equal parts, that would end up giving us the same value as pi over 2. So how will this change when we are talking about 4 times sine of x? Because your key points, are obviously going to be in the increment of pi half. So let's do those key points. So you will have 0 for the first one, then add pi halves to it, which will give us, of course, pi halves is the next one. If you add pi halves and pi halves, that will take us to pi, just like I showed you. The next one would be 3 pi halves. And the last one would take us at 2 pi. So now if you take these x values and put it into your g of x function, what are we going to end up with for our y coordinates here? So if we start with the first ordered pair, what will this give us?
Zero?
Yeah, because sine of 0 is 0. So, even if you multiply 4 into it, you're still going to end up with 0. So this actually tells us we are going to have an intercept here at 0, 0. Okay, now for 4 times sine of pi over 2. And what you guys can do is actually use your unit circle if that makes it easier. Or, of course, you guys have calculators. So you can see when the angle is 0, your sine is 0. Remember, the second coordinate is the sine function. So that's for 0. Now at pi halves, your sine value is 1. At pi, your sine value is 0. At 3 pi halves, it's -1. And remember, where you have 0, you also have 2 pi. So again, that will bring you back to this one. So you can definitely use the unit circle to help you out with this also. So what will we get for pi halves? What will our y value be for this new function? Alrighty, yeah, very good, because sine of pi halves is 1, so 4 times 1 will give you 4. Very good. Our next ordered pair is going to be 4 times sine of pi. So what will we have our y value for this guy? Okay, Melanie, you give me -4. Yeah, Andrew, Lucy, very good. Because at pi, your sine value is actually going to be 0. So you're actually doing 4 times 0, which will actually end up giving you 0 at pi. So what's happening here, guys, is at pi halves and 4 is where we will have the maximum value. But then back at pi, we will be back at the intercept. And then what will we have for 3 pi halves here? Okay, Melanie, no problem. Okay, so for 3 pi halves, what do we got? Very nice, guys. Yeah, because this is where you will be doing 4 times -1, because sine of 3 pi halves is -1. And that will make this 4 times -1, which will be -4. So this is actually where we will have our minimum value. And then what do you guys think for 2 pi? Where will we end up with y equals 4 times sine of 2 pi? Yeah, because you're back at the starting point, right? You've made that full circle and you're back where actually you started, which was the angle 0, which has now become 2 pi. So again, very nice. 4 times 0 will end up giving you 0 over here. So another thing that I want you to notice is these guys actually alternate almost. So you start at an intercept, then you can either go maximum or minimum depending on the function. So you go intercept, maximum, intercept, minimum, intercept. So that's always going to, you're going to alternate between the maximum and minimum. And, in between you will have those intercepts. So now when you actually try to graph this, and I'm going to see if I can use some of these tools to help us out. So this can be our x-axis. This can be our y-axis. Okay, so we are going from 0, 0. I'm kind of doing this without a ruler, so it may not be exactly spaced out, but let's see, pi halves, pi, 3 pi halves, 2 pi. Now remember, they wanted us to do 2 full periods. So you can either go on the positive side and do 5 more marks, or you can go on the negative side. So usually what I do for 2 full periods, I go from -2 pi to +2 pi. So this would be then, negative pi halves, negative pi, -3 pi halves, -2 pi. So 0 in the middle, pi halves, pi, 3 pi halves, and 2 pi, and then negative pi halves, negative pi, -3 pi halves, and -2 pi. So once you start graphing this, you can see 0, 0 is intercept. Then at 4, we have our maximum. So that would be, oh, this is going to be a little small. 1, 2, 3, 4. 1, 2, 3, 4. I should have made my y-axis a little bit longer, but that's okay. So +4 here, -4 here. Okay, so 0, 0 intercept. Then at pi halves, you had your maximum. At pi, we had the intercept again, so pi and 0. Then minimum at 3 pi halves, which would be at -4, and then intercept again at 2 pi. Yeah, it's a little rough because I'm not doing this on scale, but this is kind of what it looks like. So this is, again, remember, just one period. Now you cannot just do the same thing over here. You have to make sure you're doing that alternative. So since you are at a maximum here, as you're moving to the left, you will actually hit a minimum. at this point. So since this is an intercept at negative pi halves, you will actually have a minimum at negative pi will be at an intercept, and then at negative 3 pi halves, you will actually have a maximum and then intercept again at negative 2 pi. So this guy here will now go down, intercept, go up, and then intercept. And you can see that is where that repeating pattern comes. And remember, guys, this is still a sine function. You're just doing 4 times sine of x. So you're still going to have an odd function. They should still have a symmetry with respect to the origin. So everything is going to stay the same. So again, you have to alternate. You go from intercept to maximum, intercept, minimum, intercept, maximum, intercept, minimum, and then we stop at intercept. So this is what your 2 full periods will end up looking like. So the thing that's going to happen is, since we're not in class, we're not doing paper exams and stuff like that, a lot of the graphs you will be doing is actually choosing, right? And you might have seen that as you guys were working through 1.5 homework. So you have to choose the graph, but I still recommend the only thing you don't have to do is the physical drawing of the graph. But I would still calculate, take my period divided by 4 so I can break it up into 4 equal parts, do your 5 key points. So that way, at least, where your maximum, minimum intercepts, where all those points are going to fall. So I would, still do the calculation part of it. The only thing you don't have to do is the actual graphing, since, you just get to choose which the right graph will be. And, if we have to superimpose the basic sine function, so since the sine function only goes up to +1 and -1, your basic sine function would end up looking something like this. -1 here, +1 here. So this side would look something like this. So in the green is the y of sine x function. And then in the red, you had 4 times sine of x function. Okay, so sketch the graphs in the same coordinate plane, include 2 full periods. We did that, and you can kind of see the answer key for this guy. So any questions on this example over here, guys? Because the main part I want you to understand is just the process behind graphing these, right? Those 5 key points that we come up with, and then calculating your coordinates for the x and y coordinate value. So that way you can at least see what your graph ends up looking like. Okay, so Andrew, let's see, you have a question here. You can kind of think about it that way, that, yeah, you're, if you were to superimpose this on a circle, that would be a radius of 4. Because, it doesn't increase that amplitude. So, like we did the 2 times sine of x in our handout. So yeah, you can kind of think of it as, we're expanding that circle and making it bigger. But the difference is, because technically our, because technically, like I said, this would be 1 if this was a sine function, but then you're multiplying it by 4. So that increases it to a value of 4. So yeah, if you wanted to think about it in those terms, you can definitely think you're increasing the radius of your circle. That's a good way to think about it. Honestly, I've never kind of thought about it that way, but it works for sure. All righty, very nice. So you will see, various different examples on that, but now let's get into some of the other ways that we can transform. So here, all we did was honestly just multiply a number in front of our sine or cosine function. Same thing here, we multiplied it by 2. So that actually, that multiplication that you did right in the front, and I've kind of used this terminology already, is where we increase the amplitude of our function. So now we're actually getting into what we call as transformations. And you guys have studied transformations in college algebra. So, this is where we talked about translations, vertical or horizontal translation, when you're moving your graph vertically, horizontally on the x-axis, or you're physically moving your graph vertically on the y-axis. We can stretch or shrink our graphs. We can do reflection. So all of these different things that you do are what we call as transformations. And here we're giving them a little bit more of a formal name. We're calling one of the transformations as amplitude, one of them as a period, and then we'll get into some other discussions as we move forward. So basically we are saying that if you take the effects of these constants A, B, C, and D on the graphs of your equation, how is that going to change each one of your equations as you multiply by this value A, which is in front of your sine or cosine function. And this will also translate for the other remaining trig functions. What if you multiply B in front of your variable X? What if you add or subtract this value of C? What if we add or subtract this value of D? How is that going to transform our functions? And they're telling you again, if you want to do a quick review, go to section P.8 to get a review on transformations. Okay, so when we multiply our sine or cosine functions, because that's what we're dealing with right now, this is what they're calling as a scaling factor, or this is where it will basically vertically stretch or shrink your graph. And think about this, when we just now did 4 times sine of x, well, sine only goes from 1 to -1, but when we did the scaling factor of 4, you can see how it vertically stretches or shrinks your graph, so that will be based on what the value of A is. If A is positive, you are going to see a stretch. Am I saying that right? Yeah, when it's positive, you will see a stretch, and when it's, well, actually, no, I think if it's a number greater than 1, we see a stretch, and when it's a number less than 1, which will be between 0 and 1, it's a shrink. Okay, I got it now. Yeah, and that should be somewhere here in your paragraph. Yeah, so if your A value is greater than 1, you should see a stretch in your curve. When the value is between 0 and 1, you should see a shrink. And this is actually where the range of your function will then change. So instead of staying between -1 and +1, like the sine or cosine functions do, obviously your range is going to change. So if you look at this function that we just worked on, for the second function, this guy, our range actually changed from -4 to +4, whereas for the sine function, it stays from -1 to +1. So definitely the range of your function is going to change with that scaling factor that we're talking about. Okay, Andrew, not a problem. So again, guys, this is what we call as an amplitude, the A value, and basically the absolute value of A is what we call as the amplitude of the function, because it changes, how high and how low those curves on your sine or cosine function are going to go. So based on that A value, your range is going to change. So your range will then become, -A to +A, of course, including the endpoints. So just as your definition, they are saying the amplitude of A times a sine of X function or A times cosine of X function represents half the distance between the maximum and the minimum values of your function, and it's given by absolute value of A. And the reason that they're saying half the distance, because again, think about this here. You are going from -4 to +4. Well, our amplitude is going to be 4 because, if you go from -4 to +4, well, that's a total distance of 8. So you take half that distance and that gives you your amplitude. So that's what they're talking about when they say it's half the distance between the maximum and the minimum values of your function. So these next couple examples are actually just asking you to figure out, what that amplitude is going to be. And then based on that, what your key points come out to be. So this one over here, you will see we're talking about 1/2 cosine of x. So you can see since this amplitude factor is 1/2, you're actually going to see a vertical shrink in the shape of your graph over here. So again, your period goes from 0 to 2 pi because this is still a cosine function. And because this is a cosine function, your period is going to be 2 pi. Go from 0 to 2 pi, get your 5 key points, and then plug it back into this function, and you will see how my maximum minimum values change. Intercepts are still going to be at 0, but your maximum and minimum values are going to change. And there we go. It's actually this graph over here. That is your 1/2. So look at how much smaller the curve is compared to the one in the gray. The one in the gray is your cosine function, just, basic cosine function. And look, it's halfway, where the curve for the cosine is. It's about halfway where the curve for your, obviously 1/2 of cosine of x is going to be. So that's because your amplitude changed from 1 to 1/2, because this is 1 and this guy becomes 1/2. So that is your vertical stretch, vertical shrinking that happened when we use that factor of 1/2. Now in the second one, you are doing 3 times. So, in this case, of course, that means you're going to see a vertical stretch. The first one was a shrink. The second one will be a stretch. So when you again look at your, compare the two ordered pairs, this was 0, 1/2, this guy will become 0, 3. The intercepts will stay at the same value, but then your minimum will change, your maximum will change based on that amplitude. And that will be reflected in the graph. So look how different both of these graphs look. This is your 1/2, and then this is your 3. So just a matter of, using a number greater than 1 or using a number between 0 and 1. Look how different those graphs look. The general shape is the same. Your maximum, minimum are at the same x value. Your intercepts are the same x value, but it depends on how low those maximum and minimum, curves will end up looking like. So you've got another example here with the sine function. So again, if you wanted to see what these graphs look like, you can look at the video lecture for these. But I want to get into some of those other aspects of the transformation over here. So if the amplitude value that you are using, if you make that a negative number. So, in the previous example, we looked at y equals, 1/2 cosine of x, 3 times cosine of x. Well, what happens if we make that a -3? When you change that to a -3, these two graphs end up becoming reflections of each other. So just by putting that negative sign in front of that number, you are actually creating a reflection of the y equals 3 times cosine of x. And you can see that in the graph over here. So the graph in the gray is actually our positive function. And the graph in the black is your negative function. So that's the reflection. So what happens with reflection, guys? And again, if you don't remember this from college algebra, you are literally creating a reflection in terms of the x-axis. So if a point is above the x-axis, that ends up falling below the x-axis or vice versa. So here, what you will see is this point was a maximum in the positive 3 cosine of x. It actually now ends up becoming a minimum on the negative 3 cosine of x function. So look at all of these, because this is your line of reflection. You know, imagine this is where the reflection is happening. So if you place that mirror right around here, so again, your maximum was the minimum, or, you know, the minimum was the maximum. So that's how, you know, you're literally turning that entire graph upside down and creating a reflection. So that's what happens if you put a little negative sign in front of your function value. And all of this is coming from that factor of a, you know, that a that we are adding, multiplying in front of our function. So the amplitude and the reflection happens from this little a that's being multiplied in front of your sine or cosine functions. And remember, guys, that will still be true if we were doing the remaining 4, you know, secant, cosecant, tangent, cotangent functions. Okay, now we're actually getting into that factor of b. So they're saying now consider the effect of the positive real number b on the graphs of y equals a times sine of bx and y equals a times cosine of bx. So in this case, we're saying if you were to compare the graphs of just, you know, your regular a times a sine of x function and a times sine of bx functions, they're basically saying the graph of the original function a times sine of x completes one cycle from 0 to 2 pi, because remember, that's the period of the sine function. So it follows that the graph of a times sine of bx will actually complete a cycle from 0 to 2 pi over b. So actually what happens when you take this factor of b and multiply it in front of your x value, so instead of sine of x, if you have sine of bx, it's actually going to change the period of your function, because now your period will become 2 pi divided by b. And this will be true for both sine and cosine functions, because both functions have a period of 2 pi. So this b factor is going to change the period of your function. That's going to be one of the biggest things that's going to happen. And so you will see when we do these examples of find the amplitude and period, it is actually going to change the period of our functions. The other thing that happens because of this b value is, you know how we talked about the vertical stretch and shrink with the a value here? With the scaling factor, we talked about a vertical stretch and shrink. That b value will actually create a horizontal stretch or shrink. And you can see we're talking about that right over here. So we're saying, again, if your b value is going to be between 0 and 1, the period of your function will be greater than 2 pi, and it will actually give us a horizontal stretch. If the value of b is greater than 1, then actually our period will be less than 2 pi, and we will see a horizontal shrink in the basic curve of our function. So between 0 and 1, the period will be greater than 2 pi, but you will also see a stretch, you know, in the horizontal shape of your graph. If your b is greater than 1, then your period will be less than 2 pi, and this will give us a horizontal shrink. And, you know, obviously that stays true for both sine and cosine functions. Now, this one is talking about if b is negative, you will basically end up rewriting the function using those odd and even definitions of your cosine and sine function. So that's, again, where those functions being odd or even will come into play. So let's take a look at an example here. What happens with that b value? So this one here, you will see if your basic function is sine of x, this one is coming out to be sine of 1/2 x. So when you have x over 2, that's the same as 1/2 x. So this is your b value. So we can say the b value is 1/2, which means the period of your function is going to change. The amplitude is 1 because that's the number in front of the sine value. So that's going to be 1. B is 1/2, so the period will change. So 2 pi divided by 1/2 actually gives you 4 pi as your period. And we know that to be true. If I can kind of squeeze that in here. We know that to be true because they told us if your b value is between 0 and 1, then the period of your function would be greater than 2 pi. And you can see the period is coming out to be 4 pi. And we will also see a horizontal stretch in the basic curve of our function. So now that we have calculated the period and we know the period is going to come out to be 4 pi. So to find your key points, you will now go for an interval of 0 to 4 pi. So you would take 4 pi divided by 4, which gives you an increment of pi. So you will go from 0 to pi to 2 pi to 3 pi to 4 pi, because you have to end up where your period is going to be, and you have to end up at 4 pi. So just by doing this period, guys, here, you are actually already incorporating a horizontal stretch, because now we're not going from 0 to pi halves to pi to 3 pi halves to 2 pi, right? We're now jumping in, instead of pi halves, we're now making jumps in pi. So you've already skipped one of those calculations in the middle, and you're jumping 2 places now instead of 1. So we're already by default, incorporating that horizontal stretch that they're talking about here. So if you look at, how these numbers change, again, once you have your key points, plug that back into the function and then get your y values. So in this case, because your amplitude did not change and your amplitude is 1, your maximum and minimum are actually still staying at 1, which is the original range of the sine function. So your amplitude did not change. That's why your range is not changing. But now your period has changed, and you are now actually stretching out your curve. And look at the graph for this. So in the gray is your original sine function. So look, as you go from 0 to pi, we would have already completed 1 maximum, 1 minimum. But because we're seeing that horizontal stretch, look at that. As you go from 0 to pi, we just complete 1 maximum instead of doing a maximum and minimum. Same thing, as we go from pi to 2 pi, you will see again, instead of doing 1 maximum, 1 minimum, we're only doing 1 minimum, because now you're taking 2 spaces to complete that one, single curve, for the maximum, or 1 single curve for the minimum, instead of squeezing in 2 of the curves like you did with the sine function. So this is what happens when you introduce a factor of 1/2 for your b value, for that horizontal stretch or shrink. Because, obviously we basically doubled our period. Instead of pi, we have a 2 pi, we have a period of 4 pi. So you're extending it out by 2. And this one here is kind of a neat remark to help you remember, when you're dividing your period into 4 equal parts, they're saying, it's basically whatever the period of a function is divided by 4. So they're saying you can start with the left end point of the interval. So if your left end point was negative pi over 6, and going to positive pi halves, and they're saying if you have your period interval the length of 2 pi over 4, then basically, that same thing, your period divided by 4. So if your period was 2 pi over 3 divided by 4, and it, once you clean that up, it's going to come out to be pi over 6. So then your interval, start at the left end point. You're going from negative pi over 6, and then keep adding pi over 6 till you get your 5 key point. So that'll land you at 0, pi over 6, pi over 3, and pi half. So this is actually making your period a lot smaller. It's not making it larger. So just a nice remark, like I said, to help you kind of remember how these calculations work out to be. So, just make a note of that. This one here again is just asking you, what would you do if you had a cosine of x over 3 as your function? So let's pick one of those examples from here. They keep going back to sine function. Just to make a note, we're not going to spend time on this one, but if you look at number 26, it's pretty much very similar to what we did in 25. The only difference is they're introducing a negative over here. So as you can imagine, that amplitude will change to 3. So you will go from positive 3 to negative 3. But because of this negative sign here, your maximum and minimum will flip because of that reflection that will happen. So that's the only difference that's happening here in 26, is they're introducing that reflection in there. I guess we'll do number 30. I was kind of hoping, well, we've done the sine function. So you know what? Let's just use this guy as our guide here. So let's do cosine of x over 3. We'll again go to our notebook here. And we'll say sketch the graph. Okay, so let's start with the period. Obviously, remember in this case here again, guys, your amplitude hasn't changed. Let's go ahead and write that down first. So our amplitude is still going to be +1 because that's going to be the number in front of the cosine. And when there's no number, we know that number to be 1. So amplitude is still 1, which means the range of your function will not change. It will stay from -1 to +1. However, the period of our function is definitely going to change. So remember, the period is 2 pi over b. Our b value is going to be what for this function here, guys?
Three. 1 over 3.
1 over 3, yeah. So remember, the basic default is a times cosine of bx. So it's whatever number that's being multiplied into your value. So for us, this guy is 1 for the a value. Since this is x over 3, technically that means you are multiplying x by 1/3. Darren, yeah, very nice. So 1/3 will be our b value. So that means you are taking 2 pi and you're dividing it by 1/3. And I had mentioned this last time. So when you're dividing by a fraction, remember, keep the numerator the same, change that division to multiplication, and then flip your bottom number. So this will become 3 over 1. So technically you actually end up multiplying 2 pi with 3, which of course will end up giving us 6 pi. So you will see when, again, going back over here, when your b value is between 0 and 1, your period will be greater than 2 pi, and you will see a horizontal stretch. So we should see all of these things happening here. So this is now going to be our period, which is going to be 6 pi. Okay, now let's do the key points. So for the key points, you will take 6 pi. We are always dividing into 4 equal parts. What will this simplify into, guys? And leave it as a fraction, not as a decimal, obviously.
3 pi over 2.
Yeah, very nice. Just the 6 and 4 will reduce down. Darren, very good. And this will come out to be 3 pi over 2. So since they did not specify an interval, we're still using the same examples here. They're just saying include 2 full periods, but they're not giving us a specific interval. We'll still use that same idea here. And we'll, go for a interval of, 0 to 6 pi as our period interval. So for our first key point, we'll use 0. And then keep adding 3 pi halves because that's what our period interval came out to be. So 0 plus 3 pi halves will of course be here. Whatever this number comes out to be. Now with 3 pi halves, obviously you will add 3 pi halves again. So I guess we'll do this as scratch work on the side. You're going to take 3 pi halves and add another 3 pi halves to it. So what will that end up giving us?
3 pi.
3 pi, yeah, because denominator is the same. So 3 pi plus 3 pi will give us 6 pi, but then 6 divided by 2, of course, will give us 3 pi. So this third one is going to be 3 pi. Now with 3 pi, of course, we go back and add 3 pi halves. So you can think of this guy as being over 1. What will that give us? 3 pi plus 3 pi halves.
Nine pi over 2.
9 pi over 2. Okay, Savannah, Andrew, looks like you guys also had that. Yeah, because what's going to happen is we will end up multiplying this guy by 2 to make our common denominator. And you will end up with 3 times 2 is 6. So you'll end up with 6 pi over 2 plus 3 pi over 2. So 6 plus 3 will be 9 pi over 2. Very nice. And that's 4 points, so we'll need 1 more. And so for the very last one, you will take 9 pi halves and add 3 pi halves to that. So what will we get for this guy here? Last ordered pair.
Six pi.
Yeah, and this is how you know your calculations are correct, because you should always end up where your period value comes out to be. So you should definitely come back to 6 pi over here. And if you don't, that means our intermediate calculations were incorrect. So you should always have the beginning of your period, which we had 0, and then the ending of our period, which is of course at 6 pi. Now, once you come up with these values, now, of course, we need to find our y value. So we go back to the original function of y equals cosine x over 3. And we will start plugging in these x values. So cosine of 0 over 3, which is cosine of 0, what will we have for this guy? And, obviously you can always go back to your unit circle for this case. So cosine of 0 is
1.
1. Very nice, Lucy. And that's not a surprise, because remember your cosine function begins at a maximum. So yeah, it's not surprising that for 0, we still ended up at 1. You're just basically following the same logic. Okay, so got that taken care of. Now for the second one, you will have cosine of 3 pi halves divided by 3, which will come out to be if you clean this up, the 3 and 3 will cancel out, leaving you with cosine of pi halves. And what will that give us?
0.
0, because cosine of pi halves is at 90 degrees and your cosine is 0 at that point. And it's no surprise here again, guys, like we talked about before, if this is maximum, your next one has to be intercept, which means your next one has to be minimum. Next one will be intercept. And the last one will again be back to a maximum. So if you can even remember this order, it makes your life a lot easier. You can definitely do the calculations to support you. But if I know my maximum is at +1, my minimum is going to be at -1, which means my maximum again will be at +1 and intercept again will be at 0. So you start recognizing these patterns, as you go forward, and you can, again, you don't have to do the calculations. Do the calculations to make sure you're on track, and that can be something you can just throw into your calculator. But, if you start recognizing these patterns, and these, again, examples will go a lot faster for us. So I'm not going to do the calculations here. I'm just going to write down our answers. So for the next one, we had 3 pi. So that would be 3 pi over 3, which would be cosine of pi, which would obviously end up giving us -1 there. The next one, we had cosine of, I think that was the 9 pi halves. So 9 pi halves over 3. So again, 9 goes into 3 times. So this would end up becoming 3 pi halves, which would be at 0 again. And then the last one of 6 pi divided by 3 would of course be cosine of 2 pi, which would take us to +1. So let's do a quick graph over here. I guess this guy needs to go. And since we're going from an interval of 0 to 6 pi, we're not going to do negative for now, and we're just going to do one interval just to show you what the shape looks like. If you want to do 2 intervals, you can go on either side with -6 pi to +6 pi, but we are doing 0, 0, pi halves, pi, 3 pi halves, 2 pi. So 1, 2, 3, 4. 1, 2, 3, 4. This is at 2 pi. This will be at 4 pi. 1, 2, 3, 4. This will be 6 pi. Intermediate ones here will be 5 pi, 3 pi. This guy will be pi. If you had to write these guys down, this would be pi halves, 3, 5 pi halves, 7 pi halves, 9 pi halves, 11 pi halves. So those would be those intermediate values, but we are interested in 0 and 1. So let's do +1 here, -1 here. So 0 and 1 at a maximum, which is where we started at. Then at 3 pi halves, we had an intercept. So 3 pi halves, an intercept. At 3 pi, we had -1. So 3 pi, -1. 9 pi halves, we had an intercept again, which would be this guy here. And then let's see, 6 pi, we had a maximum. So 6 pi is back at 1. And remember, we have the horizontal stretch over here because our number is, 1/3. The B value was 1/3. So you are seeing a horizontal stretch. Now, if we extended this, if you double this and go to 12 pi on the positive side, you would get the two intervals that we were looking for. But, obviously, just to save time, we're not going that far out, but you definitely can. So you can see this is what that stretch looks like, because again, if we did the original cosine function, the cosine function would go from same starting point, but at pi halves, we would have, I lost my train of thought. We would have the intercept at pi, we would have minimum intercept here again, and then at 2 pi, we would have the maximum. So look how much this function has stretched because of, instead of 2 pi, your period is now 6 pi, right? So it's actually increased 3 times, and you can see how much that function is stretching out when we graph this. This is kind of what your, that horizontal stretch ends up doing. So question on this one here, guys. So when we did this one, you can see this was just 1/2, right? For that B value, you had 1/2. So the stretch here, doubled. But now, and even though this is a cosine function, we still have a stretch of 3 times. So even look how much further this guy stretches out when you compare it with just the example over here also, because now instead of 2 times, it's 3 times the stretch. So that's kind of what those A and B values end up doing. When you look at these transformations or these graphs for these transformations, how they end up changing. So if you look at very quickly, I know we're kind of out of time here, but very quickly, if you look at this examples here, they're asking us to find the amplitude and the period. So just look at this example 5 over here. You have, and let's make this guy a little bit bigger. So you have A value, which will be 2, and that's coming from this number here. Your B value is coming from the coefficient on the X. So amplitude is going to be, A equals 2, but B, remember, does not give you the period. For the period, we have to calculate 2 pi divided by P. So the period is actually going to be 2 pi over 5. And you can see that over here. So be careful. The B value doesn't give you the period. You have to do 2 pi divided by B to get your period value. Same thing if we did, let's use number 8. You've got, the A value will be the absolute value of -5. So the A is actually going to be +5. That's the amplitude. For the period, again, we have to do 2 pi over B. Can you tell me what the B value on number 8 is going to be? B value for number 8.
Pi over 3.
Yes, because only the X is not part of B. So it is going to be pi over 3. So don't leave the pi behind, guys. Pi over 3 makes the B value. So then you will do 2 pi divided by pi over 3. So just like I showed you before, keep the 2 pi as it is. Change division to multiplication and then invert the bottom fraction. And what do you think our period comes out to be here?
Six.
Yes, very nice. Your period will come out to be 6 because pi will cancel out. You end up multiplying 2 times 3 and you will end up getting 6 as your period. So just be very careful. For the amplitude, you have to do the absolute value, which means you end up looking at +5 for the amplitude. And then for the period, 2 pi divided by b, will give you the period for your function. So just to kind of get you guys started with, as you will see in your handout, we do actually then break down into, what happens when you take the C value, what happens when you add the D value at the end, how those values will change your function. So we'll definitely build up on those. So we'll pick this up next time, but I'm hoping you guys have enough information to at least get started on the first part of 1.5 homework. So again, guys, start working on that. You have any questions, please let me know. And I guess I will see you guys on Monday evening. So have a wonderful weekend, guys. Don't hesitate to reach out if you have questions, and be safe. Enjoy your weekend, and see you guys on Monday evening. Be careful, everyone. Take care. Thank
Thank you so
you.
much.
Bye-bye.